For this lesson, we're going to talk about how to find direction angles of vectors that are in standard position in the plane. If we have a vector whose initial point is at the origin, 0, 0, and its terminal point is out here at the point AB, that means in unit vector form, we would have AI plus vertical component B times J, and this is what the vector would look like. Well, there, as you can see, going to be an angle from the standard x-axis, an angle theta, that is made between the x-axis and this vector v. So the positive angle between the x-axis and a vector in standard position means the initial point is at the point of origin in the plane, is called the direction angle for the vector. So this is what the direction angle theta would look like. So we would have the magnitude of vector v times the cosine of theta, and the magnitude of vector v times the sine of theta is the horizontal and the vertical components. And so we can use these ideas to find the measure of angle theta. And we generally do this in degree mode. So if vector u is a unit vector such that theta is the angle measured counterclockwise, meaning it is a positive theta measure from the positive x-axis to the vector u, then the terminal point of u is going to lie on the unit circle, and we're going to have this situation. The horizontal component of vector u is going to be x. The vertical component of vector u is going to be y. We know that if we are on the unit circle that our x coordinate is equivalent to the cosine of theta, and our y coordinate is equivalent to the sine of theta. So this is a comma b, remember, so the coefficient a, the real number a, is the cosine of theta times unit vector I plus the coefficient, the sine of theta, times unit vector j. So the angle theta is called the direction angle for vector u. So that's where all of this information comes from. So we're going to use this idea from trigonometry to be able to find the measure of angle theta. So we have vector u, a unit vector with direction angle theta. Remember, a is the coefficient to unit vector I, b is the coefficient to unit vector j, and theta is the angle made with a positive x-axis that's in the same direction as u, positive. So vector v equals the magnitude of vector v times the cosine theta sine theta unit vector. If we wrote that in unit vector notation, then the components of vector v are going to look like the magnitude of v times the cosine of theta times vector I plus the magnitude of the vector v times the sine of theta times the unit vector j. So let's work an example. If I have vector v and I know that its magnitude, the magnitude of v or the length of v is 3, and I know the angle that it makes with the horizontal axis. Here, for example, they tell me that the angle is 30 degrees with the positive x-axis. Then I can use this relationship to actually find the components of that unit vector. So 3, which is the magnitude, times the cosine of 30 degrees. We know the cosine of 30 degrees is root 3 over 2, times I, plus the magnitude, 3, times the sine of 30 degrees, which we know is 1/2, times the unit vector j. So here is the unit vector v that has a magnitude of 3 and a direction angle of 30 degrees. So it's pretty straightforward. It looks kind of clunky, but it's really not in practice when you actually have the values. So if we knew A and we knew B, but we did not know theta, we can use this relationship to actually find what the direction angle measure is in degrees. So I know, again, let me go back here and show you. I know that the tangent is y over x. We know y is the sine of theta. We know x is the cosine of theta. When we are talking about vectors, we know we're talking about cosine theta I plus sine theta j. So we're tying all that together to be able to find what the actual direction angle measure of theta is given a vector v and given its components. So again, this looks kind of clunky, but when we work an example, you'll see what I'm talking about. We know from trigonometry that the tangent of theta is sine of theta over cosine of theta. We know that the y value for our vector is the magnitude times the sine of theta. We know the x value for our vector is the magnitude of the vector times the cosine of theta. We know here from this notation that the magnitude of vector v times the cosine of theta is going to be the coefficient to our unit vector I. We know the magnitude of the vector times the sine of theta is going to be our coefficient to the unit vector j. That's why we can say we know that this equals the coefficient to j over the coefficient to I, or simply b over a. So I can find the tangent of theta equals b over a, therefore theta would have to equal the tangent inverse of b over a. And that's how we would actually find our theta measure, our direction angle. So let's work an example. You'll see how straightforward it is. Find the magnitude and the direction angle for vector u with horizontal component 3 and vertical component -2. We know that the magnitude of our vector, based on the distance formula, is the horizontal component squared plus the vertical component squared, and then we take the square root of that. So the magnitude of vector u is square roots of 13. The direction angle can be found by taking the tangent of theta and setting it equal to the coefficient of j over the coefficient of I. So the tangent of theta would equal -2/3. Therefore, theta would be the tangent inverse of -2/3. So that's -33.7 degrees. You need to remember the plus 360 degrees. You need to remember, if you get a negative angle measure, that theta is always, the direction angle is always the positive angle from the x-axis. So if you get a negative angle measure, you're going to have to find its corresponding positive angle measure. So if I have an angle measure that's -33.7 degrees, I know that it is equivalent to a positive 326.3 degrees. So really straightforward, not difficult to do. Vector W has a magnitude of 25, so we're not given the components of vector W, we're given the magnitude and we're given the direction angle, and we're asked to find the horizontal and vertical components. We know that the horizontal component is the magnitude times the cosine of the direction angle, and we know that the vertical component is the magnitude times the sine of the direction angle. So if the magnitude's 25, we plug that into each one of these components, and if our direction angle is 41.7, for horizontal we want the cosine of that, and for vertical we want the sine of that direction angle. So we plug that into our calculator, and so our horizontal component for vector W is 18.7, and our vertical component for vector W is 16.6. So here are the horizontal and vertical components, or this is the component form for vector W. So pretty straightforward. I know when the notation gets a little involved, it can look pretty difficult, but in all actuality, it's really straightforward. So if we're given the components of a vector, it's easy for us to find the magnitude and the direction angle. If we're given the magnitude and the direction angle, it's easy for us to work that relationship backwards and find the actual horizontal and vertical components. So that's it for the direction angle lesson. Come to class next time and we'll work some homework problems.